Hello and welcome to the third video in this series. Today we are going through pressure, temperature phase diagrams. So, firstly, why are these useful? Well, they let you determine what phase is present at a specific temperature and pressure for a specific substance. This PT diagram here shows three phases: solid, liquid and vapor. We can work out which phase is present at a specific temperature and a specific pressure by reading up from the temperature axis and across from the pressure axis. In this case, a liquid is present. We can also see how phase changes can be represented by crossing the equilibrium line boundaries. So from solid to liquid, it's melting, and the reverse is solidification. From liquid to vapor is vaporization, and the reverse is condensation. And from vapor to solid, it's deposition, and the reverse is sublimation. These equilibrium lines represent points where the two phases are in equilibrium, and the tripole point is a specific temperature and pressure where these lines meet and the solid, liquid and vapor coexist in equilibrium. We can also see on this graph the critical point. The distinction between liquid and vapor can't be made, hence the equilibrium line ends. Here we have a supercritical fluid beyond the critical temperature and critical pressure of the critical point. So now for a bit of an example and extra knowledge to explain a bit about the shape of one of the curves. So here we have two solids of the same substance at the same temperature but different pressures. If we apply an isobaric increase to both solids, the higher pressure solid will melt at a higher temperature. This is because there is an increase in melting temperature for a higher pressure as the equilibrium line here slopes forward. But why is this? So first I want to explain a bit about the equilibrium of the system. As said before, the lines represent equilibrium between the phases, so Le Chatelier's principle applies. This states when there is a change of a variable or state in dynamic equilibrium, the system changes to counteract this change. For example, when the pressure increases, the system favors the process which causes a decrease in pressure. So, when you increase the pressure of a solid and liquid at an equilibrium point, the solid phase is favored due to it contracting upon solidification, meaning it has a lower pressure, so it's favored. Hence, it becomes harder to convert back into a liquid as it requires more energy to break the stronger intermolecular forces that form. Therefore, it has a higher melting point at this higher pressure solid, so it explains the positive gradient due to the solid contraction. This is not always the case though, as some substances like water expand upon solidification, so this will produce a negative gradient. We can also use PT diagrams to easily visualize cyclic processes in thermodynamics. So let's start off with a substance in its liquid phase and decrease the pressure to boil it into its vapor phase. Due to the bonds being broken in phase change, latent heat is taken in from the surroundings, causing a temperature drop, which as a result causes deposition to occur. During this phase change, latent heat is released instead, increasing the energy of the surroundings, causing temperature to increase and a repressurization due to something called the condensation effect of deposition. This combined effect causes melting to occur and a return to the substance's original phase. Therefore, there's a cycle. This is called cyclic equilibrium, which occurs via a self-regulating mechanism. Understanding this can help us understand what happens at the tripole point, where the temperature and pressure is just right for these processes to happen simultaneously, allowing the three phases to coexist in equilibrium. Okay, so thank you for watching this video on PT diagrams. Goodbye!